Okay. Hello to every one of you. Welcome back to the AESP 314 class. Today we are going to finalize chapter 2 and we essentially are going to solve some example problems. These example problems are from your book. Some of them are the previously solved examples by the book, and some of them are the problems at the end of the book. Keep in mind there's something that I have to mention, is that I was going over the solved examples of the book and I was looking at the solutions provided by the authors, that there are some mistakes in the solutions to the examples that are provided by the authors. Okay, and these mistakes can be a little misleading. I just want to make sure that you are aware of these mistakes. Okay, so without any further ado, let's jump into the examples and the solutions to those examples. The first problem we are going to solve, and what I'm going to do is I'm going to write the text of the problem and then we're going to solve it together, right? So we have air that enters, this is the first example, a constant area combustion chamber at a specific Mach number, at Mach 3, at a pressure and temperature of, a total pressure and temperature of PT1 equals to 45 kPa and TT1 is equals to 1800 K respectively. Yeah. And the fuel inside this combustion chamber is hydrogen. So hydrogen with a lower heating value. The reason we chose hydrogen as a fuel is because it has a lower value of heating value compared to the other elements, so it will burn sooner, right? It will be the first thing to burn. And it has a heating value of 120,000 kilojoules per kilograms, kJ or kg. Okay. So we are asked to find the exit total temperature if the exit is choked. So we are dealing with total conditions. And we are also asked to find the maximum heat release per unit mass of air. Q star. We are also asked to find the fuel to air ratio F to thermally choke the combustor exit. And we are also asked to find the total pressure loss in the, that's total, so we are looking for the PT loss. total pressure loss in the combustion chamber, in the supersonic chamber. Okay. So as you can see, we have a constant area duct with heat transfer. So the first assumption you can make is that you are going to neglect the wall friction because you have heat transfer. It is constant area, so it resembles Rayleigh flow. So we are going to treat the fluid as an inviscid fluid or inviscid flow in general. Okay. And therefore we are going to have Rayleigh flow. Okay. The second assumption we usually make when we are dealing with combustors is that the mass addition to the combustor due to the fuel flow rate is very small. Compared to the inlet and airflow, essentially, right? And we eventually finally assume that the burner has 100% efficiency. And then with using these assumptions, we can start solving the problem. So the first thing you need to do is to go to Rayleigh flow tables. Of course, these tables are located at the end of your book. So I have a PDF version of your book here. It's essentially going to be your appendix D of the book, right? As you can see, you have M at the first column. You have P over P star. That's the pressure over the pressure at the sonic condition. T over T star, rho over T star. And also you have the total pressure and temperature ratios and delta S over R. Something I forgot to mention in the problem text was that your gamma here is 1.3, and that's the effect of fuel, right? So you cannot assume it is 1.4 anymore. And your R is 0.287 kilojoule per kilogram Kelvin. Okay. And we have two types of tables here. Rayleigh flow for gamma equals to 1.4, and then the Rayleigh flow for gamma equals to 1.3, which is exactly located after the first table. Okay, so we can use these tables to we can use this table for the inlet condition. The inlet condition is M equals to 3. Okay, so for M equals to 3, you go to these tables. Rayleigh table, right? We have M equals to 3 here, right? You have the pressure ratio, temperature ratio, density, total temperature, and the pressure ratio. Again, we are looking at for these two parameters, pressure ratio and the temperature ratio, because we are asked to find the total temperature, total exit temperature, total temperature at the exit, and total pressure loss. Okay, so these are the two things that we are looking for, which essentially means that temperature ratio is 0.603 and pressure ratio is 4.00. Okay. So T1 over T star is going to be 0.06 0.6032, and P T1 over P star is going to be 4.0073. Just a small note here. I usually, in order to avoid any confusion, I usually write P as this and rho as this. So whenever you then see this at the end of something that looks like the P, it is a rho. Okay, so this here is the thing that tells you that we are dealing with pressure, not density, right? So we have these two pressure and temperature ratios. We have the total temperature exit to be 1800. So 1800 over T star is equals to 0.6032. So your T star, which is going to be your exit temperature, because we wanted to choose the exit. We wanted to find the condition where the exit is choked. Okay, is going to be roughly equal to 2984 Kelvin. Okay. The next step is to find the maximum heat release per unit mass of air. So the total heat release is, of course, can be found. We are going from TT1 to sonic condition. So your maximum heat release is also a star, is Cp multiplied by the delta T. So TT star, and this is the total temperature. TT star minus TT1. Okay, delta T. But we don't have the Cp. How can we find the Cp? We have the R and we have the gamma. We already know that Cp equals to gamma R minus gamma minus 1, which means that it is equals to 1.3 multiplied by 0.287 over 0.3. So it will roughly be equal to 1.2437 kJ or kilojoules over kg Kelvin. Okay, and we have the delta T because we have the two temperatures. Your Q1 star can be calculated to be 1472.6 kilojoules per kilogram of air. So that's kilogram of air, not kilogram of fuel. Keep that in mind. We're neglecting the mass of the fuel. So the next part is the fuel to air ratio, F. How can we find this fuel to air ratio? It is actually pretty simple. To find that fuel to air ratio, you have to multiply this F, the fuel to air ratio parameter, by the heating value of your fuel, which in our case, it was given in the problem. And it will always be given to you. 120,000 equals to the total heat rate. Okay, which is 1472.6. So this will give you a value of 0.0123 for F, which is equals to 1.23%. Okay, fuel to air ratio, pretty simple. And this is the fuel to air ratio for the thermally choked combustor exit, right? And the last part, which is part D, is asking us to find the total pressure loss. Okay, to find the total pressure loss, we essentially are looking to find the delta P of total pressures over PT 1, which essentially means that we are looking at the PT1 minus PT star over PT1. Is equals to 1 minus PT star over PT1. We have the PT1 over PT star. We have read that from the table, so we are going to have 1 minus 1 over 4.0073. So your total pressure loss is going to be equals to 75%. You have lost 75% of your total pressure to heating, essentially. So this is the first example. This was an example of the Rayleigh flow. Again, the next example is also an example of Rayleigh flow. So we have a subsonic flow in a constant area duct, of course, which is subjected to heating or to heat transfer. We have the inlet parameters. M1 is equals to 0.5 subsonic flow. Total pressure 1 is 14.7 psia. TT1 is equals to 50 degrees Fahrenheit. Gamma is 1.4 and R is equals to 53.34 feet pound force over pound mass degrees Rankine. Okay. We are told to neglect the wall friction. So Rayleigh flow, again, heat transfer, constant area, neglecting wall friction means we are dealing with the Rayleigh flow, and we have to calculate the new inlet Mach number. M1 prime if Q is equals to Q1 star. So essentially this is telling us that your Q is higher than your sonic or choking heat rate. Okay, what happens when you have this condition on subsonic flows? You're going to get some backflow, and eventually your flow will stabilize with some spillage around the duct. Okay, and your new exit conditions is going to be the new sonic parameter, right, for the new inlet parameters. And then we want to find the percentage of spilled flow at the inlet. The first thing you need to do is to convert the degrees Fahrenheit to Rankine, to absolute scale. You just have to add everything, every temperature we have by 460, which is going to be give you 510 Rankines. Then we want to go back to the Rayleigh tables for gamma equals to 1.4 in this case, not 1.3, and find the temperature ratios, because we want to calculate the sonic heat rate, right, for this specific inlet. T of t minus TT1 star, right? We have seen this before. This is also a star. Okay. So let's go back to the Rayleigh tables for gamma equals to 1.4. We are looking at the Mach equals to 0.5, so subsonic conditions here, right? This is your total temperature and pressure ratio. We don't really need the pressure ratio here, do we? Yeah, we don't really need it, but just take the temperature ratio, the total temperature ratio here. That's it. Okay, and let's go back here. For that, you can find the total temperature ratio to be, I'm sorry, let's go back there. Mach equals to 0.5, so your total temperature ratio is 0.69136, right? .69, forgot the number, 136. Okay, so we essentially can find the TT star here pretty easily. It's gonna give you the I'm sorry, TT star is gonna be the TT1, which is 510 over 0.69136. Okay. I don't have the final value for the TT star here because we don't really need that, right? In this calculation, we can just take one TT1 out, and is going to give you, this is going to give you TT star over TT1 minus 1, right? Which is 1 over the ratio you already have. So this is 1 over 0.69. And the solution in your book has actually used this method as well. So the other parameter we need to calculate is your CP. Again, gamma R over gamma minus 1. CP. Okay, 1.4 multiplied by 53.34 divided by 0.4. So this is going to be give you 186.69 feet, pound force, pound mass, degrees Rankine. Okay, so using these values, and we have the TT1 510 Rankine, we can find the Q1 star to be 42,505 feet, pound force over pound mass. Okay, so this is essentially for this specific inlet, this is the value you are going to get at the exit. This is the heat rate you're going to need to get a choking condition at the exit. But we say the Q1 we have is 1.2. The QM 1.2 multiplied by this Q1 star, right? So it is higher. It means that it doesn't really mean anything for your exit condition. Your exit condition is still choked, but you're going to get some spillage and backflow. That's the idea. So let's calculate this new exit condition, which we are going to call Q1 star, Q1 prime star, if you will. Is going to be C equals to CP TT1 prime star minus TT1, right? So here, your total exit temperature is going to change because your Q is changing, right? But your total inlet temperature will not change. Total inlet temperature will not change. Okay. So we are looking to find the new total exit temperature, which if you rearrange these equations, you are going to find Q1 prime over CP, right? We have the CP, you have the TT1, you have the Q1 prime star. That's essentially just 1.2 multiplied by whatever you have, which should be equals to 51,006 feet pound force over pound mass. Okay, you plug in the values, 510 Rankine, 51,006 over 186.69, which will give you roughly the value of TT1 prime star to be 783 degrees Rankine. So what we do here is we are going to find the new total temperature ratio for the prime condition. Is going to be 0.65116. So we wanted to find the new Mach number, M1 prime, right? We have this pressure ratio. We go back to the Rayleigh tables. We find the value for 0.65116. We are looking at this part of the table. So 0.65116. So this is essentially going to be somewhere between these two. You do an interpolation to find the M1 prime, which has to be between 0.46 and 0.48, right? After doing the interpolation, you'll get the M1 prime to be roughly equal to 0.473. That is going to be your new Mach number after the adjustment has done. Okay. But how can we find the percentage of the spilled flow? The percentage of a spilled flow is essentially M1 dot, whatever M is coming in, M prime 1 dot, like the mass flow at the inlet, the new mass flow over M1 dot, right? Multiplied by 100. And you have to keep in mind that the total conditions, total pressure and temperature remain constant between states. State 1 and 1 prime. So we have this parameter because total conditions remain constant at this specific case, where your heating Q is larger than Q star, subsonic flow, and you're going to have a spillage, right? Because of that fact, the mass flow in both cases is essentially proportional to a parameter, the mass flow parameter F of N. How can we find this mass flow parameter? This mass flow parameter is essentially m divided by 1 plus gamma 1 minus 2 m squared over to the power gamma plus 1 over 2 gamma minus 1. Okay, so essentially we can do fm1 and fm1 prime. We can find those two, and your flow split is going to be fm1 minus fm1 prime over fm1. If you calculate the values, you plug them in, you're going to get 0.439 minus 0.4148 over 0.4319. Okay, which means that your flow spillage, inlet flow spillage, is going to be 3.966%. So 3.966% of the flow will spill over the duct because of this condition. Okay. So let's solve an example for the case of fan flow. The example states that air enters a constant area duct of a circular cross section with a diameter of 10 centimeters. So this is your hydraulic diameter because you are dealing with a circular cross section. The length of duct is L equals to 20 centimeters. Okay, duct is insulated, so no heat transfer, constant area, no heat transfer, means that we are dealing with the fan flow, right? And the flow is of course assumed to be adiabatic. The average wall friction coefficient, C of F, is 0.005, and the inlet Mach number is M1 equals to 0.24. Okay. The first thing you would need to find is L1 star, the choking length of the duct, then M2, your exit Mach number, the percentage of total pressure loss, so delta P of T over P of T, and static pressure drop, as well as the loss of fluid impulse due to friction. Okay, so we have M1 as 0.24, right? This time we need to go to the Fano table. Fano tables are Appendix E, and your gamma here is assumed to be 1.4, so we're gonna go to this table, right? The Mach number is 0.24, so we are looking at this row for all the parameters. We are going to read the parameters. Let's write them here. One of the first table gives you 4CF L star over D to be 9.3866. Total pressure over PT star is 2.4956. Pressure, static pressure, is 0.4 the ratio 4.383, and the impulse ratio I star is 2.043. Okay. So using this ratio here, we have the hydraulic diameter and we have the CF. We can easily find L star. L star is roughly equal to 46.933 meters. So what does this mean? This means that we have our duct will not reach the choking condition, right? Because the duct length is 20 meters, not 20 centimeters, sorry, 20 meters. Okay. We want to find the exit Mach number. So if you recall, what we did was that we assumed to find this. This is your real duct, and this is a case of L star larger than your length, right? So we assume that imaginary duct that starts at the exit of the first one and ends at the choking condition, right? L star, L1. And L2 here is L star minus L1. Okay. And this is L2 star because it will get to the choking point, right? So L2 star is equals to L1 star minus L1 or L. So 46.933 meters minus 20 is going to give you 26.933 meters, right? So using this new length, we have to calculate the ratio of 4CF L2 star over the hydraulic diameter. Nothing has changed except for the L2 star. Plug that in. It will give you the ratio of 5.3866. And going back to the table, for this ratio, this is the first column, right? We are looking for 5.3. So between, essentially this one, right? Between this and this, right? But we are going to assume that the 4CF L star over D is 5.299. So your exit Mach number is simply or roughly is going to be 0.3. Using that, we can find the ratio of the total pressures with the sonic condition 2.0351. Also the ratio of the static pressure, which is going to be 3.6191, and the ratio of impulse, which is going to be 1.69. Okay. The next part has asked us to find the total pressure loss and percentage. So delta P, PT1 minus PT2 over PT1. If you divide everything by a PT star, it will be PT1 over P star. And these are all P's. PT2 over P star. And PT1 over P star. And to find the percentage, we have to multiply this by 100 as well. So plug the values in. We have all the ratios. You just need to plug the values, and your total pressure loss is going to be roughly 18.45%. Okay. The static pressure loss, or the static pressure drop, is essentially going to be exactly the same, calculated the exact same way as this, except for static pressures. That's it. It's divided by P star multiply it by 100, plug in the values, and you're gonna get 20.25%, right? So the last part has asked us to find the loss of impulse. So I2 minus I1. Which we can find as a factor of I star. 1.698 minus 2.43. So we divide everything by I star. That's what I meant, right? Divide and multiply. So what you're going to get is I2 over I star, I1 over I star multiplied by I star, right? And these are the ratio, 2.43 multiplied by I star. And then we can simply find the loss of loss of impulse as a factor of the sonic impulse, right? So we're gonna lose some impulse, so this is going to be negative 0.345 multiplied by I star. Okay, and that's it. That's it for this problem. The next problem is going to be a supersonic flow, right? This is going to be about the one that we discussed in class, and I'm sorry. Yeah, this is a thing we discussed in class, and it made a little confusion in the class. So we're gonna solve an example about it. Okay. Let's see. So this is the problem. We have to consider supersonic flow, okay, of an air in a long duct. No heat transfer, constant area, with friction. So Fano flow. Okay. We are given the duct length to diameter ratio, L to DH, is 40. The inlet Mach number is 2.6, and the average wall friction coefficient is given to be 0.005, right? We first are asked to demonstrate that a normal shock will appear in the duct and then calculate the location of the normal shock. And then draw the TS diagram for this type of flow. Okay. So in order to demonstrate that the normal shock will appear, you essentially have to show that your L star is smaller than your L. So the choking will happen. This is a supersonic condition. We will have a normal shock wave. Okay, but we don't have the L. So we essentially have to work with the ratio of this. So we are going to find this L1 star over the hydraulic diameter. So we are going to work with the length to diameter ratios in general. For M equals to 2.6 and gamma is 1.4 here again, right? Supersonic condition. 2.6 fan of flow. This is your condition. You can have the pressure ratios, whatever you need. CF L star over D. Okay. For M, M1 equals to 2.6. This ratio is going to be equal to 0.45253. Okay. So L star over D is going to be equals to 22.62, right? L star over D, L1 star over D is smaller than L over D, which was 40, right? The diameters are the same. It means that L star, L1 star is going to be smaller than L. So we will definitely have a normal shock. Okay, so what do we need to do? We need to find the location of this normal shock, right? The idea is this normal shock happens somewhere with L of X. We have to guess the value of the shock, of the Mach number, just downstream this shock wave. Okay, M, which is called M of X. Let's assume M of X is equals to 1.5. Okay. Then for this M, we go back to the Fano table to find the 4CF Lx star over D ratio, which is, if you go back to the table and look at it, it is going to be equal to 0.13602. Okay, so for this Mach number, Lx star must be equal to 0.13, right? Which essentially, let's cut this again. Essentially, what we are doing here is that we have an M1, we have an Mx, which is acting as an exit Mach number. So we have found a star parameter for it, right? Lx star. Of course, we are just finding the ratios here. And we want to find, and we already have the L star over D. So the star condition, using the inlet, we want to find Lx over D. Okay. So using this, we can find the Lx star over dH to be I don't have the final calculations for this, but we don't need actually to have the final calculation. We can actually say 4x. The idea is this value Lx over D is equals to L star over D minus Lx star over D, right? Lx over D is equals to this minus this, right? We can multiply all sides by 4CF. We have the value of 4CF, we have the value of ratios. You eventually will find the Lx over D. I'm sorry, my pen is acting out again. So Lx over D, which is going to be equal to 0.31651. Okay. So this is going to be your Lx over D. So what I'm going to do is I'm going to delete this imaginary table. And then this is the length ratio before the normal shock, right? Lx over D. But we have to find an Ly as well, Ly over D. For the real duct, not the imaginary duct, right? So what we need to do is to find My, which is the value of the Mach number downstream the shock wave, right? How can we find the value of the Mach number downstream the shock wave? You don't need to use any of the equations in general. Same is true for the Fano tables. You just need to find the proper table. So appendix C. Normal shock tables. M1 coming in, which is Mx, right, which is assumed to be 1.5, right here. And the value of M2 is on the second column. So My is going to be 0.700011. So after the normal shock wave, your M1 is going to be 0.7011. Okay, then we essentially, let's cut this half of the duct this time. Okay, the Y half. You essentially have a duct with an inlet Mach number of 0.7011, a subsonic duct, pretty simple, right? And you want to find the length of it. But we already know that this length is the choking length. That is the idea, right? Because the normal shock happens and the choking happens. Because the choking has happened inside the duct, we have the normal shock for the flow adjustment, right? So that the exit condition will be the star condition, M star equals to 1, right? That was the idea of choking in general. Okay, so we already know that Ly is Ly star, right? So you go to the Fano tables, which is appendix E again, right? Look for Mach number 0.7, which is here, and then find the ratio of 4CF L star over D. So this will give you the ratio of Ly star over the hydraulic diameter to be 0.081. The next step is to add the Ly, Lx and Ly star and see how it compares to L. Just compare it to L, right? We can multiply all sides of equation, this comparison, by 4CF over the hydraulic diameter. So you can essentially, you are gonna get the same thing, right? So we are going to have 0.31651 plus 0.2081, which is the value here and the value we calculated here. I forgot to mention that this is for CF, right? And for CF, for the duct, for CF multiplied by L, for the duct is 4 multiplied by 0.005 multiplied by the ratio, which was 40. This will give you 8.8, sorry. And this side will give you 0.5246, right? So this is much smaller than 0.8. We want it to be as close as possible. What does this mean? It means that the value of Mach number we have chosen is a small, or it means that your shock wave is very weak. So we move to the next step. Step 2, guess mx again, but this time, since this 0.5 is smaller than 0.8, we wanna have a stronger shock, which means that we are going to have a faster flow with a higher supersonic case. So for this faster flow, we have to do everything from the beginning, right? We essentially have to find Lx over d, which was the same case again, right? Same case as before. Let me actually go over it again. So let's cut the M1 going in, right? Let's cut the duct again into, we're essentially cutting the duct at the shock, right? So your inlet here is gonna be, outlet is gonna be Mx, inlet is gonna be M1, right? And the assumption here is that we haven't reached the choking condition yet. Okay, so you go to Fano table for this one, you read the for CF Lx star, which is this length, over dH. This ratio is 0.03495, and we already have the length L star from the previous analysis. That's 4CF L star over D. That ratio is 0.45253, right? And we want to find this Lx, or we want to find 4CF Lx over dH, which is equals to 4CF Ls star over D minus 4CF Lx star over D, right? So this value for you is going to be, if you do the calculation, plug in the values, pretty simple, 0.14758. Okay. So this will give you the ratio for this part. This is not an star. This is an X. Okay. But then let's find the Mach number using the normal shock tables after the shock wave. So your My is going to be equals to 0.5774. As you can see, this is a stronger shock wave. And then we have to find the star condition for this Mach number. We assume the Mach number to be 0.58. Using the Fano table, you can find, and we are finding the Ly star over dH ratio. can always go back to the previous step. It's essentially a repetition of the previous step with new numbers, right? And this Ly star is going to give you the ratio. And again, we have to check whether compare Lx plus Ly star with your length. Since we don't have the length, we are going to compare these ratios. Okay. We already know that this is 0.8, and we know that this is 0.14758, and this is 0.572. Did I give you the correct number? Yes. Okay, so this addition will end up being 0.7233, which is still smaller than 0.8, right? But it is much closer. So for the next step, I'm not going to go over the next step because it's essentially the same thing, the exact same thing. So for the, if I had told you that I want the error to be smaller than 10%, which means that the difference has to be smaller than 0.1, right? This would have been an acceptable solution. But if I have told you the error must be smaller than 0.01%, which means that your value you're calculating here should be 79, between 79 and 0.81, 0.79 and 0.81, then you should go the other step, and you should, since your value is still smaller than 0.8, you need a stronger shock. But this time a little stronger, not that much stronger. So you can choose 2.1, which has your book has chosen, and do the analysis again till you get closer to 0.8. But this is how it goes. This is how the iterative method essentially goes. For the TS diagram, you essentially, if I ever ask you to draw the TS diagram for this case, you have to keep in mind that you have an M1 inlet and an MX before the shock wave, MY after the shock wave, and MS star M1, right? So you have to read the delta S over R for these values as well as the temperature ratios, okay? And if you were to calculate, if you were to plot this, one of the axis will be T over T star, the other one is S over S minus a delta S over R essentially, right? You start from 1 here, and we had the Fano line. You start from point 1, supersonic condition. You go to the point X, which is before the normal shock. Then the normal shock moves you to the upper line, which is the subsonic line. So this is the subsonic line. This is the star condition, right? Subsonic. And you can find, if I ask you to draw this, you have to find all of these values, right? So it shouldn't be an approximate. So 1, X, and then you have the after the shock, the supersonic on this line, right? And then it will get you to the star condition at the outlet. So this is how a TS diagram would look like for this case. Okay. And this is, honestly, this is the hardest, if you will, the hardest question you may face. I will give you some homework problems from the impulse part calculation and the wall force analysis, which is essentially which is going to be the variable area case, right? So for the variable area duct, adiabatic, no friction, I'm going to ask you to find the force that wall exerts, force that wall exerts on the fluid, right? And if you recall, that is related to your impulse. Okay, so make sure to read the other examples. But let's solve two examples from the normal shock wave, and then I think we have already passed the 1 hour and 15-minute mark. So you don't need to, if you were in a class, you could have just, we would have dismissed the class, but since we are not, I'm going to continue. And of course, you can watch this is as many sitting as you like, right? So this problem, we are dealing with an oblique shock wave, with a reflected oblique shock wave. So your shock wave has essentially has collided with the wall and has been reflected. You have the M1 coming in at 30 degrees, region 1, region 2, region 3, and you have the fluid turns 9 degrees after this shock, and then it is straightened out again. Okay, so we are given this geometry, and we are asked to find M1, M2, M3. Okay. It may look like an odd question to you because we don't have any of the inlet properties, but we only have two angles, 30 and 9 degrees. But if you recall from the lecture, that based on the theta beta m relationship, we can actually, if we have the two of these parameters, we can find the other one. And we already have two of the parameters. Your beta is 30 degrees here, and your theta, your turn angle, is 9 degrees, right? So what do we need to do is go back to this plot here and essentially find the Mach number that is related to the beta of 30 degrees and delta theta of 9 degrees. Okay. If you do so, you will find m to be 2.6, right? So we are looking at the beta of 30 degrees, right? And this is the M 2.6 line, right? As you can see, yeah, I can definitely draw here. This is the 2.6 line, I guess, somewhere here. I will go to 9 degrees, right? You don't need to use this plot. You can just use Google, essentially, to find the calculator. But this is how you do it. And we usually are usually dealing with the weak shock wave part. So we don't really deal with the strong shock wave part unless you're told to. Okay. So your M1 is going to be equal to 2.6 using that table. This table is also in your book. This figure, I'm sorry. This figure is also in your book. It's figure 2.23. If you don't have the book and if you need me to post the appendices, please let me know. Please send me an email. And yeah, but you can always Google everything, like Fano table, Rayleigh table, the normal shock tables, all of them are out there. Right? And if you recall, after finding these three properties, right, theta, beta, and m, we had to find the normal component of that, normal to the shock, normal component of that flow, right? So M1n, which we could calculate by multiplying M1 by sine of beta, okay? Sine of beta is sine of 30 degrees. So it's 1/2. So m1n is going to be equal to 1.3, right? And then for this 1.3, you go to the normal shock tables, and which was, I think, appendix C, right? And find an m2n. That's the normal to the shock, right? You can find this to be 0.7860. Okay, pretty simple. And then we can find m2 to be m2n over sine of beta minus theta. Okay, beta minus theta is 30 minus 9, so sine of 21 degrees, right? And m2n is 0.7860. So your m2 is 2.193. So we are still going to be in the supersonic shock regions. And we have a reflected oblique shock with an m2, and we already know that theta is 9 degrees because it is straight again, right? So the flow was turned 9 degrees, and it's going to turn 9 degrees back, right? So you go to the table again, that figure here. This time we have the m, so these are the lines of m. That's 2.19. Let's say 2.2. So this line essentially, and we have the theta to be 9 again, and you find the beta, which is roughly 36.5 degrees. So using that, we can find the normal to the shock component of the microwave in the second region, m2 sine of beta. Plug all the values in, you can get m2n to be 13.5. And then you take this value to the normal shock tables, and you can find the m3n to be 0.7860. To find m3, you're going to use this equation, m3n over sine of beta minus theta. That's 36.5 minus 9. Therefore, m3 is going to be 1.7.2. So we have all of the things that we needed to find. Let's solve another example from the final example from the expansion wave analysis to see how those problems work. And then we are going to finish this lecture. Okay. So we have this kind of corner. We have the expansion wave that has a degree delta, right? Your theta here is 30 degrees. Okay. Your M1 is going to approach 2.0. And then we have M2, of course. The area this streamline covers is A2 after the expansion wave. The area it covers before the expansion wave is 1, and we're talking about a specific streamline, right? So it is a supersonic flow that expands around the sharp corner as shown in the figure, and we are to calculate M2, the area ratios, and also the angle. Let me write it down. The angle of Prandtl Meyer fan or wave. envelope. Okay, which is this angle delta. So whenever you heard this, what is the angle of the Prandtl-Meyer fan envelope, we are talking about this angle, right? So it's essentially the angle the first Mach wave makes with the last Mach wave. So how can we find this? Of course, since we are all dealing with tables, here we are going to have a Prandtl-Meyer table as well. But the first thing you always need to do is to establish the wall turning angle. Or nu 1 M1 first, right? For before this shock wave. You go to the Prandtl-Meyer table at the appendices at the end again. Here, the approaching Mach number is 2, so you find Mach 2. Your V, your nu for Mach 2, the turning angle is 26.36, and your mu Mach angle is 30, right? So nu 1 of M1 is equals to 26.38 degrees. And then mu was 30 degrees, right? We are not going to use mu at this point. We're going to use it later. The first part is asking us to find M2, right? So we want to find, we also have V1, nu 1. I'm sorry, I don't know why they keep calling this V, right? So we want to find nu 2. We want to see if it's possible to find nu 2. If you recall from the lecture, your theta was essentially this angle was nu 2 minus nu 1, right? So we can find nu 2 as nu 1 of M and 1 plus theta, right? We have 26 degrees, 26.38 degrees plus 30. So your nu 2 is 56.38 degrees, right? And then you go back to this table here, you find the 56.38, which is between these two values. So you either do that in interpolation, or you just assume, you can just take M2 is roughly equals to 3.4. So you can see after an expansion wave, your flow is going to be faster. So let's get to the second part of the problem. How can we find the area, this area A2, the ratio between these two areas, A2 and A1. Again, A1 is the area that this streamline makes with the wall, and A2 is the area that the same streamline makes with the wall. That area is going to change after an expansion wave. Okay, so how should we do this? It's pretty easy. This time we need to use the isentropic tables. And find the value of A over A star, right? A star is the area a specific streamline makes with the wall during the sonic condition, right? Keep in mind, I don't know if you have, I have a feeling like that we didn't really go over this, the areas, but keep in mind that these areas are arbitrary streamlines. We don't need to have a specific streamlines because we are dealing with the ratio of the areas. So let's say you are you are working on with this streamline, which is A1 prime, right? The ratio, the area is gonna be different, but the ratio of the areas are gonna stay the same. So it doesn't matter what area you have chosen, which streamline you have chosen, and what area you are calculating. Since we are not dealing with the real area and we are dealing with the area ratios, it's gonna be staying the same. So let's go to the isentropic tables this time. Isentropic tables are, I think, Appendix B, or yeah, Appendix B. Yeah, exactly. Appendix B. So you come here, you can see that you have A over A star as the fifth column. M1 is 2, so we have to go to the here, fifth column. This is going to be your area ratio, 1.6. And M2 is 3.4. So we have to go further here, 3.4 here. And your area ratio is going to be 6.18, right? So A1 over A star is going to be 1.678. A2 over A star is going to be 6.1836. And we are looking to find A2 over A1, so we just have to divide this by this, right? And A2 over A1 is going to be give you 3.664. But how can we calculate the fan angle? Here we are going to need to find the Mach angles, right? The Mach angle we have already seen from the table is 30 degrees for downstream. And if you go back to the Prandtl-Meyer tables and look for Mach 3.4, you will find the second Mach angle to be 17.10 degrees. So we have the Mach angles, which are the angles the waves make with the wall, right? So your delta, that's the angle between the first Mach angle and the last Mach angle, is going to be theta plus the difference between the two Mach angles, right? So to show it on the, let me actually draw another one. So you have this mu1, okay, and you have this mu2. Okay, that's actually the angle it makes with the flow, right? So it's a little, this is your mu1. Sorry. And then you essentially subtract these two and add theta. 30 plus mu1 was also 30 minus 17.10, which is going to be equals to 42.9 degrees. So you have the Prandtl-Meyer fan angle as well. I think this is it for the lecture today. And have a safe week. We'll see you on Wednesday.